We move on to yet another kind of statistic, a single mean. How do we test this? How do we build a confidence interval for this statistic? So what is this kind of statistic? Let me recap the kinds of statistics we've seen so far in hypothesis testing and confidence intervals. A difference in proportion is exemplified by controlled trials. An alternative hypothesis would be that vaccines can prevent polio. There are two proportions, the infected proportion of the control group and the infected proportion of the treatment group. The sample statistic is the difference in proportions. The null hypothesis says that there is no difference in proportions, but the alternative hypothesis says there is a difference in the population. We then moved on to single proportions. This is still a categorical variable, but no longer a treatment control comparison. The alternative hypothesis is usually a threshold. Say at least 30% of the lodgepole pine trees in BC have been infected by the mountain pine beetle. The null hypothesis is no longer just zero, but it's the negation of this threshold, that 30% or fewer are infected. These were both for categorical variables. Now we want to do statistics for numerical variables. For numeric variables, we measure means, averages. The alternative hypothesis will again be a threshold, but now a threshold of a mean, not a proportion. Something like the average length of an adult female blue whale is at least 21 meters. The null hypothesis is again the negation of this, that average length is no more than 21 meters. This is the kind of statistic I want to study now. The approach will be similar, hypothesis testing and confidence intervals. We're going to find a distribution, figure out our means and standard deviations, use that to construct z-scores, percentiles, p-values, and confidence intervals. Though the approach is similar, working with numerical data is different. It is a bit more complicated than working with proportions. It's not just yes or no, success or failure. Instead, numeric variables take a whole range of values. That means that the population itself looks like a distribution, not just a single percentage. We're trying to figure out something out about a pretty complicated situation. The population distribution is, like the population parameter before, the actual situation out in the population, and we have no idea what it looks like. It could be some strange distribution like this, with peaks and valleys and patterns and whatever. There's no guarantee in particular that it's a normal distribution or any other kind of distribution for that matter. So how do we investigate it? Well, we'll use the tools we have for distributions. And for now, we'll stick to just two of those, mean and standard deviation. All distributions, not just the normal distribution, have means and standard deviations. We'd like to use the sample to determine something about the population mean and maybe the population standard deviation with some confidence or by testing some hypothesis. This is what we're trying to do. Do be careful now. This is a population distribution. It's how the actual unknown entire population looks for the values of a certain variable measured on that population. We'll be looking at samples and then randomization as before, and the randomization will create a sampling distribution. It's important to keep the difference in mind. There is a population distribution and a sampling distribution, and they are not at all the same. Again, I'll use an example to set this up. We'll talk about the length of adult female blue whales. Say we managed to measure 20 such whales in the wild, and we got this data. This is our data set. We want to figure out what we can say about the general female blue whale population based on this data. We're going to need a sample statistic. There are in fact two, the mean and the standard deviation. I've calculated them here. The sample mean is 23.358, which I will write as x bar for the rest of this video. The sample standard deviation is 2.116. Note that this is always standard deviation. I will never use the term standard error here. The term standard error is only used for sampling distributions, not for population distributions. From this point, for either hypothesis testing or for confidence intervals, I could proceed by bootstrapping to make a sampling distribution for either the mean or the standard deviation. Then I could compare my sample statistic with the distribution to determine a p-value and a confidence interval. As before, we're not going to do the randomization anymore, and instead, we're going to use probability theory to supply us with the distributions and the process for calculating p-values and confidence intervals. So the mathematical theory will give us the distributions. For the previous sampling distributions, I applied the central limit theorem to say that if I did enough bootstrapping or data shuffling, my sampling distribution will be normal, so I can just use the property of the normal distribution. The same does apply here. If you do enough bootstrapping randomizations, then the sampling distribution will be normal. But again, there are conditions. I didn't talk that much about the conditions before, but I want to here since they are potentially more common. What I need to avoid are samples with significant outliers. If the sample size is small, then any significant outliers can cause the central limit theorem to fail. If the sample is large, then the system is a bit more robust and only very extreme outliers are a problem. In my example, the sample is small, only 20 whales. The data points 19.3 and 26.7 were the bottom and the top of the range. They didn't seem too separated from the rest of the data. Maybe they are significant outliers, maybe not. But maybe I am a little bit worried. What do I do if I'm worried about the application of the central limit theorem? Well, there is a solution. And the solution is yet another kind of distribution. The t-distribution is something quite similar to a normal distribution, but with a couple important differences. The red curve here is a normal distribution, and the others are t-distributions. Look specifically at the blue curve. Compared with a normal distribution, this has larger tails. This is what a t-distribution does. It models something like a normal distribution, but allows for more substantial outliers in these larger tails. Like the chi-squared distribution from the last video, t-distributions have a parameter called degrees of freedom. The blue curve here is the t-distribution with only 1 degree of freedom, the green is with 2 degrees of freedom, the orange with 5 degrees of freedom, and the red curve, which I said earlier was normal, is actually the t-distribution for 100 degrees of freedom. As the degrees of freedom increase, the t-distribution becomes more and more like the normal distribution. So for large sample sizes, the two become basically the same. Therefore, the t-distribution is useful particularly for smaller sample sizes, like the 20 whales in this example. As I said, for larger sample sizes, t-distributions and normal distributions are nearly identical, and statistical methods will produce almost exactly the same p-values and confidence intervals. Okay, once I've chosen a t-distribution, the setup and the process are still more or less the same. I want to talk about means and standard error, percentiles, and p-values. I want to figure out if a sample statistic is within 95% of the data or not. I want to determine the middle 95% of the data for a confidence interval. So what is the mathematics to do this? As before, the probability theorists have studied the t-distribution and produced calculation techniques for us. Let me guide you through them. First, for hypothesis testing and p-values. I have a sample statistic for the mean, 23.358 meters. I have the null hypothesis, that the population mean is 21 meters or less. I have the alternative hypothesis that the population mean is more than 21 meters. I'm going to need the standard error again. Unlike the square root expressions before, the standard error is easier to calculate here. It is the standard deviation of the sample, sigma, divided by the square root of the sample size. For a normal distribution, once I knew the standard error, I calculated a z-score for my sample statistic. That was a measure of how far out the sample statistic was in the sampling distribution. Eventually, how unlikely it is under the null hypothesis. Here, for t-distributions, there is something similar, and it is called a t-score. It is defined in basically the same way. The sample mean minus the mean dictated by the null hypothesis, divided by the sample error. For normal distributions, if I have a z-score, I calculated its percentile, either from a table or by R, and used that percentile to generate a p-value, either as that percentile or as 1 minus that percentile, depending on which side of the distribution I was on. Here, there is a calculation that goes directly from a t-score to a p-value. Historically, this was done again with tables, which were called t-tables. We'll just use R. I asked R, and it gave me a p-value of 0.000367. Obviously, this is a lot smaller than 0.05, so by the usual threshold of significance, this is a significant result. I conclude that this sample gives evidence that the mean length of adult female blue whales is over 21 meters. The null hypothesis is rejected, and the alternative hypothesis is supported. To recap, this is the process. Calculate the sample mean, state the null hypothesis with the threshold value you want for this mean, calculate the degrees of freedom, R will need that from you at several points, calculate the standard error, calculate the t-score, and finally use the t-score and the degrees of freedom to get a p-value. When we did hypothesis testing with normal distributions, we had to worry about 1- and 2-sided tests. The same is true here. In the example about blue whales, I only did a 1-sided test. However, 2-sided tests are also possible. The process is the same as before. If I want to make a 1-sided test into a 2-sided test, I just double the p-value. Visually, I'm looking at both sides of the distribution, so the likeliness of being somewhere in one of the two tails doubles. The unlikely range is now only 2.5% of each side, not 5% of one tail. Finally, let me talk about confidence intervals. I have the same starting information, the sample statistic, the degrees of freedom, and the standard error. The setup for confidence intervals, as before, is an interval that starts below the sample mean and ends above it. The distance out is some number times the standard error. For 95% confidence for a normal distribution, this number was 1.96. And that number, again, comes from probability theory. Historically, again, you would have to look that up on a table, and for us, we will let R calculate it for us. The same is true here. All t distributions for various degrees of freedom have these numbers that determine various confidence intervals. I didn't define this number last time, but they are called point estimates. The point estimate for 19 degrees of freedom and 95% confidence is 2.09. And again, I just asked R to calculate this for me. Therefore, the confidence interval here is the mean minus 2.09 times the standard error, up to the mean plus 2.09 times the standard error. And in this case, it works out to 22.396 to 24.374. What does this mean? It means based on this sample, and as always, assuming the study doesn't have any bias or confounding variables, I am 95% confident that the mean length of adult female blue whales across the entire population is between 22.396 and 24.374 meters.